Good morning, everybody. I can't see anymore, but I guess you are here. My name is Florence Rivière-Bourris, and I will moderate this panel today. What? Closer, okay. So I give a brief introduction. Okay, we're gonna get there. So about this panel, in the 90s, we said capabilities related to the four technologies of the IMS and to OSI were reviewed, and their pertinence for the objective of the treaty were assessed through a number of exercises to be finally carved in stone in the treaty. However, the treaty protocol several paragraphs which allows for, first, the possibility for the IDC to perform an expert analysis upon a state request, and with data provided by the state, and also a paragraph which offers the possibility to member states to cooperate with the organization in order to improve the verification regime using additional monitoring technologies. So now we are 30 years later, and research has improved and led to new development and new technologies that could prove useful for the purpose of both the IMS and the OSI, specifically for this expert analysis. And what will be discussed here today are examples of such new technologies, how they could contribute to enhance the CTBTO capabilities to achieve its goal, and the framework required to use these technologies. So how it's going to go, I'm going to give the floor to each of the panelists for 5 minutes, and I've prepared questions, one question for each of them, and at the end we would be left with about half an hour where we would take questions from the floor. So we're going to start. First panelist is Laurel Sinclair from Natural Resources of Canada. Mrs. Sinclair has been trained as a particle physicist and spent 15 years at Natural Resources Canada, leading a program of research to support nuclear emergency response mobile radiation survey. She's currently occupying the position of chief scientist at the Canadian Hazards Information Service. Please, you have the floor, Laurel.
Thank you. I'm very happy to be speaking to you today in, I think, nearly the final panel session, second to last final scientific panel session of the conference. This position on the last day of the conference enables me to put my remarks in the context of some of the great presentations and discussions that I've been a part of earlier this week. One of the themes that I've been exposed to that struck me as particularly important is the need to reduce bias in decision-making by the on-site inspectors in an on-site inspection. And this is actually the perfect lead-in to the technology that I want to present to you today, which is about helping the on-site inspectors to make unbiased decisions. Slide?
No,
oh, it's me. Okay, it's me. First speaker. Where do I point it? Oh, there. All right, so let's just look at the image that's on your left. My experience is in nuclear emergency response and in nuclear security exercises. And what we've done here is we have a very large volume of gamma-sensitive scintillating material placed on a truck, and we go out to see what we can see along the road, through the woods, up the road, around a loop, and come back. And now we need to interpret that data, which shows the gamma intensity measured by that detector in the truck. And we see two locations on the loop where there's high intensity recorded of gamma intensity. And there are a number of possible interpretations. You could say, oh, well, there's radioactivity on the road in those two places. That's one possible interpretation. If you're a little more clever, you may say, oh, no, there's radioactivity in the middle. It's just one source, and it's radiating in two directions. But in fact, the number of interpretations of that data is about infinite. There are many different places that you could put a source that will give rise to that data. Okay, slide. Oh, it's me again, sorry. All right, so now we're looking at the image on the far left. The mobile survey detector that we took on that loop is actually a gamma imager. So we've taken that volume of scintillator material, that volume of sensitivity that allows you to make a spectrum every second, and actually turned that into a gamma imager. So now we can look on that loop using the gamma imager. So if we just look at the one image on the far left, what does that show? Does it show that there's a gamma source inside that hut? It actually does not. But for many people, that image is so concrete that is the conclusion that they want to arrive at. In fact, the gamma source can be anywhere between the gamma imager and that hut and beyond. It could be 200 meters beyond that hut. You don't know where the source is from that image other than it's somewhere in that direction from the gamma imager. Now, if we go around the loop and we take another image, that's the one shown in the middle, now we can start to kind of do a triangulation in our mind, and we really know where that source is, and our confidence that it's in the hut is very high. So what I wanted to show in my last image that I wanted to show is the one on the left here. And what we've done there is kind of reproduce an on-site inspection scenario in which there's a restricted access site. So the gamma imager has been placed at all the points where there are red triangles. It's taken images at all of those points. And now we have a top-down view of those images. So we're showing them geographically in a tomographic method that allows us to combine the gamma images from all of those different perspectives. It's a sort of triangulation, but a triangulation that permits reconstruction of a distribution rather than a simple point. And we arrive at the conclusion, the correct conclusion, that there is radioactivity in two locations with two different magnitudes. And this is the product that we think is something that could be very useful in OSI.
Thank you, Laurel. You are done?
Yes.
Okay. So my question is, given this gamma imaging technology, how would that perform with radionuclide, CTBTO relevant radionuclide?
Okay, thank you for that question. The CTBTO relevant radionuclides span a range of different energies. And the approach that we've taken is to use scintillator that's segmented in many different pieces that allows us to do a Compton imaging approach, which is extremely effective for all energies from about 200, 250 keV and up. For the much lower energies, there are different technologies that are relevant. The technology that we've been exploring is just to use the fact that detector is self-shielding. There are crystals on one side which shield crystals on the other side, so you can still reconstruct a direction. You can still do your triangulation and your tomographic reconstruction of a distribution, even if you're in a situation where there are only some very low energy radionuclides present.
Okay, thank you for your presentation. I'll move to our next panelist, and it's going to be Jamie. Jamie is from the Atomic Weapon Establishment in the UK. She's a lead for on-site inspection, coordinating the contribution to CTBTO across the government, military, academia, and public sector. She has a background in geophysics, reading earth science at Oxford, and then defending a PhD in Martian seismicity, please.
Long time ago.
Jimmy is also the team lead for the UK National Data Centre on wave foresight, and has an excellent team of researchers and analysts working to improve our understanding of event analysis. So, Jimmy, please, you have the floor and the remote control.
Thank you very much, and thank you for the opportunity to speak today. So I will be talking very briefly today about the potential of novel seismic methods in the context of on-site inspection. So really, I just wanted to highlight with this slide the dual nature of progress in any field. We have the incremental improvement versus the seismic shift, novel innovation. So this is the kind of analogy of, you can invent brighter and better candles, and you can improve your candle technology, or somebody can invent a light bulb. And I think it's very important to make sure that we have a balance of these two things. So to ensure that we are making progress kind of step by step on the technologies that we're all very familiar with, particularly in the context of the treaty, but also that we are open and welcoming of these new methods insofar as possible. So in terms of incremental development for geophysical methods in on-site inspection, there are a few different avenues that we can go down for this. So market research into improving techniques and equipment. We can run field trials of new and developing equipment. We need to be very responsive to developments, and also the basics like software upgrades, and just to really make sure that we are kind of keeping abreast of those developments. And in that context, earlier this year in May, the UK hosted a CTBTO geophysical equipment field trial where we deployed several geophysical techniques. There were several different technical objectives for this field trial. These included, for example, new to market seismic equipment deployment to test how that acts against equipment that we already have in the equipment pool for on-site inspection. Really developing the efficiency of our deployment strategies and data flow, and really ensuring that everything that we have already is really nailed down and efficient as it can possibly be. And then you can just see here on the photos, there's an active seismic survey and then like a drone image of our survey line. And then in terms of the kind of seismic shift, broad innovation, we really are living right now, and I'm sure every generation feels the same, but in this kind of time of very rapid technological development, and there are several new light bulbs in this area. You can see them there on the slide. I've just picked out a few of them that we should be researching, thinking about, learning, adapting, particularly in the context of OSI. So INSAR and multispectral imaging, the use of drone platforms, machine learning, and then novel seismic imaging. And I'm aware, obviously, in the context of the treaty, that some of these are a little bit controversial, and we'll need some time to think and develop how to incorporate these into an on-site inspection. And the example that I really wanted to highlight, this is some work that a student of mine did in the past few years on time-lapse seismic monitoring. And he was really looking at the potential of using this method in the context of an on-site inspection. There are various potential signatures for time-lapse seismic, including the thermal signature following an underground nuclear explosion, the pressure signature, and how that kind of moves out through the rock, and the damage zone, and then groundwater mounding and flow if you are kind of interacting with the water table. He found the first two of these signatures were kind of too short-lived, but that the groundwater flow signature, which is analogous to the oil and gas industry, monitoring for movement of oil and gas in the subsurface as they extract, that was relevant over on-site inspection timescales. So he kind of really dug into that method, and I think it is, it has real potential for on-site inspection. And I will pause there and move on. Thank you.
Thank you, Jenny. Question, what would be the pros and cons of this time-lapse seismic monitoring in the framework of an on-site inspection?
Okay, thank you for the interesting question. I think the pros, once you are at the kind of the site investigation stage of an on-site inspection, you've narrowed down your site location to one or two areas of interest. This technique could really help you locate the cavity very quickly and very efficiently over several days once the equipment is established. I guess the con in this scenario is the intensity and the time it would take to actually deploy the survey. And I guess it would be quite disruptive to other techniques as part of the inspection as well. So whilst it is a very powerful method and we should really explore it further, in the context of an inspection where you have a limited time and limited capacity in your inspection team, this is a very high intensity technique. So you would need to be very sure of what you were looking for before you deployed this method.
Okay, thank you, Jenny.
Thank you.
We move on to our next panelist, which is Michaela Fry, and he moves the remote control. Okay, Michaela is from the Federal Institute for Geoscience and Natural Resources, BGR, in Germany. She is the head of the Remote Sensing Working Group at BGR and a member of the German Copernicus Expert Group. Main research interests are synergies of optical and radar remote sensing and remote sensing-based application. She is a leading initiator for the initiative and development of the European Ground Motion Service. Michaela, you have the floor. Thank you.
Thanks very much for the invitation. Thanks for the introduction. And thanks to Jenny, she already raised the point, INSAR and multispectral methodologies or data for the aspects of nuclear tests monitoring or detection. And I want to introduce the aspect with these few wordings. What is the background? How can we use spaceborne optical and radar remote sensing data to characterize tests? And what is the way towards the ground truth of nuclear tests based on satellite remote sensing? And I would like to show you these on examples from the North Korean nuclear tests, where we investigated data to show displacement maps in 3D from the test from 2016 to 2017, and also landslides related to the test in 2017. Why I'm going to show you these different data sets, which is already also laid down in the publication mentioned here, in multi-technology analysis of the 2017 test. Why I'm going to show you these different tests. You are going to see in this slide, I'm starting in the order of the left upper image. We have investigated the different tests in the 2 years, and they are based on radar data of different sources. Though the left upper is based on the Copernicus Sentinel radar data, the right upper is based on RadarSat, on the Canadian radar satellites. On the upper left, you see the image which is based on ALOS-2. And on the right-hand lower side, you have the change detection map based on optical data on Pleiades. So why was this necessary? Because when we started to study the test, we realized that even so, we have, with the Copernicus Sentinel, an operational sensor with the RadarSat operational and also ALOS, we do not have the data, all different types of data sets in this time frame. Because what we needed or what we wanted to do is we had to have data sets directly before and directly after the test to show the impact. And what you see here in the blue colors, these are the subsidence. It's a subsidence which is counted in centimeters. So blue is subsidence of between 6, 7 and more than 10 centimeters. And this is why we had to use the different data sets. And on the left lower hand, we did use ALOS-2 data, which is a longer wavelength data. So the RadarSat and Sentinel is 5.5 centimeters. The other one is 23 centimeters. So we had a huge impact on surface, and the C-band, the lower frequency, did not show any coherent results. So we investigated the longer wavelengths. So it was not only because the data were not available, but it was also because the data did not show, due to the huge impact on surface and the huge subsidence and uplift in the region, no coherent signal. Superimposed on the lower left are the epicenters of the nuclear tests, which were analyzed by seismics. And on the right-hand side, you see the landslide map, which is based on optical data of high resolution. My last slide, I would like to talk a little bit on the technical background, on the principles of the INSA, differential INSA and advanced differential INSA. On the left hand, you see the basics. We have two acquisitions, data acquisitions of the radar signal, which is coming back from surface. As soon as we have a ground motion in time, we have a different in the center, in the middle, you see the principle of the phase shift, so we get a phase shift, and this is used to do the change detection, to do the INSA modeling on that. This was done with two image pairs for the tests I did show you. On the bottom in the center, you see what happens if we have a multi-temporal data sets in time over many years. We do a so-called persistent scatterer. And this is then shown in a product which results in, we have mean velocities and we have displacement time series. This is done in ground motion services like the European Ground Motion Service. And on the bottom, you see the time series from 2015 to 2022. So we have change detection in time. Thanks.
Thank you, Michaela. My question is based on your study you did on the North Korean event. How can these techniques be more systematically applied to test detection and also to OSI?
There are two ways to do that. First of all, we have at the moment, we have a lot of different sensors in space, not only radar but also optical sensors. We have impressive coverage, a global impressive coverage already there. So we have, like for the Copernicus Sentinel data and also for RadarSat with C-band, we have a very good coverage already. So it's likely that we have these, if there is in terms of a test, that we can produce these images. For data like the longer wavelengths, this is not globally, we have no real persistent global coverage. Even so, ALOS, we have a lot of data already, but we will have an L-band sensor in space in the Copernicus fleet also soon. This is set, so we will have multi-frequency radar data available globally, which allows also then to detect and monitor different kinds of impact on Earth's surface. So if we have, like in the 2017 September test, we had a huge impact which with high subsidence and movement rates, so I'm confident that we will go there. We also have lower frequencies which are not yet globally available in X-band with 3 centimeters, but we are going there. So this will be the way forward into these directions. And if you talk about site inspections, we have a lot of data available, and we know that for site inspections, remote sensing data are used for preparation for before the site inspection's done. And my aspect is always to use synergies of different methodologies and analysis products in synergy together to get the most holistic picture of what happened. And this was done also here. We did use different methodologies, so we went in this direction of multi-technology applications.
Thank you, Michaela. I will move to our fourth speaker, Konstantino Litovski. Please get the remote. Yes. So he's from the French Atomic Energy Agency, has been doing research in the field of atmospheric science since 2010. He spent almost 10 years working on cloud microphysics and related atmospheric dynamics issues in the planetary atmospheres and polar regions. He joined the Atomic Energy Commission in 2019 to work on middle atmospheric dynamics in the context of infrasound studies, focusing on the modeling and observation of the middle atmosphere, infrasound data analysis, and comparisons with propagation simulation. Konstantino, you have the floor.
So thank you, Florence, for the introduction. Thank you for being here to attend this panel, and thank you for the invitation as well. And so, yes, so I wrote down here a few key messages. Of course, all of them could be discussed for hours, but we don't have hours. So I will be speaking of LiDARs, but from the perspective of infrasound technology, one of the technologies used in the IMS. And so it's important to have in mind that I guess the main point was already raised on the discussion panel on 3D propagation modeling on Tuesday, when it was said that the big problem we have essentially is the atmosphere, is the propagation medium. And so because on the long range, across long distances, infrasound will be guided through waveguides established between 0 kilometer height and 150 kilometer height, up to the thermosphere. And it's very difficult to account for this medium, especially that meteorological models and numerical weather prediction models are very biased in the middle atmosphere, essentially because of a lack of data to constrain their data assimilation system. And it's a fair point also because those models generally focuses on the surface weather, not on what's happening in the middle atmosphere. And so this is why we may think that of a way of accounting for the atmosphere in a statistical way. However, we may think also of a way to increase the amount of information by using instruments which allow to constrain what is happening in the middle atmosphere by observing all the waves, planetary scale waves, internal gravity waves, which propagate and will actually interact with the infrasound wave fields propagating. And so this information, because essentially when you are localizing or characterizing an event, you need a wind model. If you want to do it in a good way, you need an efficient wind model. So here's an example on the left, which shows an output from a numerical weather prediction model. Zonal wind, top line, bottom line is the meridional wind, and you see on the right LiDAR observations, same location, same time, and you see everything that is essentially missed by a numerical weather prediction model, a state-of-the-art one. And so those biases that the model have can really prevent from efficient characterization or localization of infrasound sources. On the left, there is an interesting vertical profile showing the zonal wind as a function of the altitude. And here what you can see is that literally sometimes a numerical weather prediction model can just totally miss what is actually happening in the middle atmosphere in terms of waveguide. So you may just have a wrong waveguide if you only based your diagnostics on a state-of-the-art middle atmosphere model, or say atmospheric model accounting or simulating the middle atmosphere. And it will highly affect the way you propagate the waves in a model, and so the way you want to account for for instance, if you want to localize your infrasound sources with a wind model. And of course, so the LiDAR is even be able to be useful for just to state whether there is a waveguide or not. It's not just about resolving all the details of the atmosphere, but also about stating if there is a guide or not that allow the infrasound wave to propagate across long ranges. On the right side, I just wanted to remind that when it comes to energy estimation, one needs to have amplitudes of gravity wave perturbations, for instance, which are realistic. So all the colored lines are like these little wriggles are gravity waves which are here parametrized to try to reproduce an observation made here at the Tunisian station, IS-48, of the Beirut explosion. And above the red line, which is observation below, you have several attempts to model the waveform based on several realizations of gravity waves in the atmosphere. And it's difficult to do this tuning, or it would be much easier to do this tuning with ground truth information as it can be obtained from the LiDARs to better constrain the way to determine energy for events of interest. Thank you.
Thank you, Constantino. So I think you led almost to the question, what other technology would you need to take care of the limitation of the LiDAR at the altitude useful to treat infrasound events?
So what the LiDAR can do, I mean, there are plenty of LiDARs. What the LiDAR can do here for our matter, what we're interested in the middle atmosphere, they can give you information on the temperature and on the winds. This is what we really want to have. And depending on the channel, you may be sensitive to the very lowest altitudes, even down to 5 kilometers above the ground, using the Raman scattering, inelastic scattering. With the Rayleigh scattering, you're okay, you're good to go above 30 kilometers till 90, 95 kilometers, depending on the way you are post-processing the data. And you can also hit the lower part of the thermosphere, for instance, using metallic atom resonances, and for that there are like iron LiDARs, sodium or potassium LiDARs, so they can observe at a very high cadence. So you can go down to a profile every 5 minutes, which allows to resolve in details the perturbations that propagate into the middle atmosphere, like for instance gravity waves. There is a point which is problematic with LiDARs, is that as soon as you have clouds, you get blind. And so to alleviate this, there is something which was nicely shown during a European project that gathered many countries to try and assess systematic biases of middle atmosphere models and to show the added value of instruments for the infrasound community. So this was the ARISE project, the Atmospheric Dynamics Research infrastructure in Europe. And so the idea of the project was to show that one can use LiDARs and radars, for instance, to efficiently monitor the state of the atmosphere from the ground to the thermosphere, or to a part of the thermosphere at least. And so there are, for instance, wind radars that can work even with a cloud cover, even with a dense cloud cover, and so they can go together quite nicely with LiDARs to provide constraints on the middle atmosphere, even though the LiDAR is not observing at this time. And so I wanted also to point to a nice presentation that was done on Tuesday, I think, on the Korean infrasound bulletin. And what they showed, so they were using a ground-to-space model, which has been developed by Drob et al. In 2010, I think, which is a hybrid way of approaching the atmosphere with operational outputs between 0 and 50 kilometers, and reanalysis between 50 and 80, and above that, a climatology. And so what it was shown during this presentation about Korean infrasound observation is that sometimes those kind of models will not allow you to understand the data you have at the station. And then you need weather information on the local weather in the instance I'm referring to for this presentation. And what they show is that they were not using LiDARs, so they were using a wind profiler and a radiosonde sense. And they showed that by constraining their propagation model not with an atmospheric model, but with observations, ground truth from a wind profiler from 0 to 5 kilometers, I think, and a radiosonde ascent from 0 to 30 kilometers, they could really well explain their observations. So it does show the added value of remote sensing or in situ observations of the atmosphere to constrain our understanding, localization, and characterization of the sources. Thank you.
Thank you, Constantino. Then move to our last but not least speaker, Johannes Otz from Leica System in Switzerland. Johannes is a global business lead for BLK ARC, a high accuracy SLAM-based, so it's simultaneous localization and mapping LiDAR for robots. Johannes is also master in geodesy from the University of Karlsruhe, and is an expert in combining laser scanning on robots. Please, you have the floor.
Thank you, Florence. Thank you very much for inviting me, giving me the opportunity to present what we are doing here in our organization. And I think what was a very, very interesting, thus simple slide was from Jenny, her first slide, where she was saying that there are different ways to innovate. There is the incremental steps, where you continuously improve a solution, but then there is always this big thing, the big next thing, as you all remember, I think, when the new iPhone came out, I have the next big thing. But there is also other ways on how you can innovate, and this is something what I would like to present you in the next 4.5 minutes. These are ways on how you can innovate if you bring technologies which are proven from other markets into a new application and into new fields. And this is what we currently see here. Robotics has risen in the last 3, 4, 5 years massively in the construction industry, in the automotive industry, in the chemical industry, in the oil and gas industry. So this is getting a proven and used technology. LiDAR sensors, a little bit different what Constantino was sending as a message out. We develop LiDAR sensors that scan while you move. So you create a 3D digital model while you walk through an environment, a tunnel, a nuclear power plant, a facility, this room. So within minutes, you can create a very accurate 3D representation of this facility. So how can this improve site inspections? I think the key element of these workflows is that you are fast and safe to collect data. Your workers are safe when they go into very dangerous zones. The robot goes into this one. The operator stands on the safe location. So this is an incremental innovation step, but a massive innovation for an industry like on-site inspections. So SLAM-based means that you navigate the data through the environment and access a danger zone. So what you can see here is a little video from a mine. This is a customer of ours, and they collected hundreds of meters of mine shafts within minutes. So the collection time was around 15 to 20 minutes, and this is what you get as a representation of your shaft. It's an almost photorealistic 3D representation, highly accurate. Here we are talking about an accuracy of few centimeters, 10 to 20 millimeters. With these opportunities, as I said, you collect data in a short time, and I believe on-site inspections must happen fast. The data delivery must happen fast. And this is something what we as Leica Geosystems are used to provide as a solution to our other customers. They are also interested in get the digital twin fast and accurately. So this is something what I believe on-site inspection is a massive advantage. But it doesn't stop there. I'm not saying that I have the next big thing, but I think we are partnering with a company out of the UK. The company is called Triatech. They are very strong in nuclear, especially in nuclear power plants. So what you can combine is a sensor fusion. So you can use the position of our sensor. As I said before, it's a SLAM-based. The SLAM-based means we always know very accurately the position of the sensor in space. Then we can combine this one with a radiation imager, as Lauren mentioned before. This one then can combine in dose plans. So here, this is a video shown from Fukushima. This is a very important information that you get in a very quick amount of time to see where the radiation sources is. If you walk through this one, you will recognize very easily what the problems are and what are the consequences, and you can make fast decisions. But what is faster than a few minutes? Faster than a few minutes is real time. And this is what we also have newly released together with our partners, a solution. This now shows gamma radiation in real time on a video stream. So this is not only that you have the awareness that there is gamma radiation, you also have the awareness that the gamma radiation, where it is located. This is, for example, from Sellafield. These are pipes who are showing gamma radiation. And this technology is heavily used now in various nuclear power plants, either those ones where there was unfortunately a core mold, but also in operating power plants. So this is something where my 5 minutes, I think, are over.
Yes.
And thank you.
Thank you, Johannes. My question is, okay, all this technology and this digital twin imaging can be applied in the framework of the CTBTO, the 3D, and the OSI, for instance?
Absolutely. So I'm not sure if you are aware of this word digital twin. Digital twin is something which is a very common phrase now in many industries. The digital twin there's always a very nice saying in the construction industry. You always build a building twice, first virtually, then digital, then real. And the digital twin shows the real world in a digital world. And the base for that one is the point cloud. The base for that one is an accurate representation of the reality. But then the digital twin requires further information that helps the user to make decisions. In this case of the nuclear power plants, where is gamma radiation? Where can people walk safely through with maybe contamination suits? But on the other hand, where are no-go areas for the human? Where is it too dangerous? So these are the elements where you can apply information to the point cloud and feed it with much more additional information. And this is what we are heading for with our technology.
How far can your robot move from the person who is operating it?
Excuse me?
How far can your system move?
Yeah, it's a very good question, because on robotics, you can either operate autonomously or teleoperated. Autonomous means that we send the robot into a power plant, and he walks through autonomously, given on a path we define and tell him in advance. But very often you have a very unknown terrain, like in 3 Mile Island. This is a survey we did, totally unknown, very high CVAS values, inaccessible for humans. So there you operate teleoperated. This means you have a remote control, you have mesh radius, and you can send the robot far, far away. Inside buildings, tunnels, nuclear power plants, we experience something like 300 to 500 meters. You can guide the robot teleoperated. On open field, you can do this one over tens of kilometers partly with a mesh radio technology.
Thank you, Johannes. Okay, Thank you all. We are done with the formal presentation. And I am blind. I can't see anything. But if you have any questions from the floor, I would gladly take them. You are supposed to use microphones if you have questions. So, are there any questions to the panelists? Yes, no? If no, we are done.
Yes, we have one.
I'm sure they are.
Oh, yes, okay. Thanks for moving to the microphone.
I have two questions. The first one refers to Laurel's last slide. If you can put it on again. And while you're doing that, I'll give my second question to the LiDAR presentation. How much local LiDAR information can yield information on a long route of propagation of a signal? Do you need like a dense a network of LiDARs in order to get the proper information to analyze the signals? So I'll go now to the...
Can we get the presentation from Lauren? It's coming?
I'm coming. It's coming.
Okay. It's just... Sorry. Can you repeat the question, please? Because we were trying to...
There was a two-part question,
so
right? I
the last slide of Laurel showed some analysis that, as was pointed out correctly, might lead into wrong conclusions. And I think that here we see very nicely three elements that might influence the conclusions that inspector reaches. One is what you measure. The second element is how you analyze the measurements. And the third one, and I think this demonstrates it very nicely, is how you present the results to the user, to the inspector. So presumably, like if you look at the left side picture, what you see is a projection of two-dimensional contours on a three-dimensional scene that was taken in a two-dimensional image. And then the human brain is automatically, he knows, or she knows how to interpret such information by making the projection and reaching the conclusion. So what I think this shows is that it's not less important than what you measure and how you analyze the data, also how you present it to the user and what is the interface to the inspector in order to bring him to make the best use of the data.
Yeah, absolutely, absolutely. And to speak a bit, to reinforce that point, indeed, the gamma images can be very, they're a little dangerous on their own, because the assumption that the gamma source is co-located with something in the environment that the inspector recognizes could be a false conclusion. And it's okay to suggest that as an hypothesis, as long as when you write up your little report saying it appears, it's in the hut, you make note that that hypothesis, that hypothetical conclusion, includes information from the detector and information from your own experience as a human, that people tend to do things in huts. If you make those 2 points clear, that putting these two pieces of information together, I've arrived at this conclusion, then maybe it's got some basis to be believed. And was there another?
Maybe let me just add one comment here as well, even though the question was to Laurel. I think that demonstrates very, very nicely why I am a believer in 3D, not 2D, because representing this kind of information on a 3D model will definitely ensure that it can be viewed from any kind of angle, and there is no source of error that we can see on a 2D space only. And that's why I believe the sensor fusion of these different technologies, what Laurel was presenting as a 3D image, or combining with a point cloud, I think that's the future, as I strongly believe.
Okay, let me, if I could just respond to this one a little bit. I love what you're doing with the point cloud. It's very well advanced, and I can see how you're building on the expertise of Leica with the lensing and the imaging, and now bringing in the LiDAR to make that 3D point cloud in real time. That's fantastic, very useful in a situation where there might be a crumbling building or something like that. But again, I'm afraid that what is happening a bit is that you've just translated the problem of projecting a gamma image onto a 2D image into the problem of projecting a gamma image onto a 3D image. That's again dangerous, and I've actually seen this in a situation where a room was being reconstructed that had, or a whole building that had contamination through it. And it doesn't matter that you've made a 3D model of that image and shown the radioactivity on the wall of a room in that building, it still might be well behind that wall. So what you need to do, and we can do this, we can work together on this, I think it's really exciting, is you need to separately do that tomographic solution to figure out where the radioactivity is, and then superpose that on your point map. But don't project the radioactivity onto the point map unless you're admitting that you've made an assumption that it's on that surface, because it could be on a subsequent surface.
Absolutely, and that's why it's very important that you do a complete scan. Huh? That you do a complete scan not only of one room, that you see the other room as well, and then you can source this and combine it. I fully agree on that one, yes.
I hope this answers the question or complete the statement. Thank you very much. Next question, please.
Florence, actually there was a second question.
There was a second question. Sorry.
On the LiDAR. So thank you for raising this point. So the question was related to the fact of the LiDAR accounting for local conditions, and not necessarily regional conditions. Well, actually, it depends on the wave you are looking at and the waves that are at stakes. If you take like even internal gravity waves propagating, they will have like characteristic length scales which may span 100 or 1,000 kilometers. And so even just with a single point, actually you can have a decent amount of information on what is happening at the regional scale. Now you can look at also under a different perspective. You can also consider that the LiDAR, I mean, you won't necessarily be using the LiDAR as your wind model, but as a constraint to the model you are using to do your 3D work, to bring better uncertainties, for instance, on the model, atmospheric model you are using. Now, having said that, and what is interesting is that recently, and I guess in the last decade at least, portable LiDARs have been developed that are a bit less expensive, easy to move around. And so it's not absurd to think of a network of LiDARs to be put in clever places. And so there have been concepts thought of developing LiDARs that are efficient and less costly. And so it makes sense to think of a network of LiDAR, but you wouldn't need it to have it like every 10 or 20 kilometers, but every, I don't know, 500, 1,000 kilometers, or every 2,000 kilometers, at every infrasound station. But literally, you do get a lot of information just with a single point, even though you are looking at regional sources.
Sorry for.
No, it's fine.
Thank you, Constantino. Yes, sir. Next question.
Hi, I'm Harry. I wrote an online question, but after all this discussion of LiDAR, I'd like to refine it. And also, I realize that several people have spoken about LiDAR. I'm interested in wind profiling LiDAR, and I think the gentleman just really answered my question. But I'd like to point out, in OSI, we have a 1,000 square kilometer area to worry about, and it's not unreasonable to put a LiDAR at each of the places that you're doing, say, seismic aftershock modeling, monitoring, or other things, to have a handful of LiDAR, exactly as he said, to pin down the weather in your inspection area. But I would like to address a point that Dr. Sinclair made about biases that inspectors have. We absolutely have them. I was a second cycle inspector. We absolutely have them. We're trained to recognize them. We still don't. But what happens is a visual observation team will go to a site and they'll say, there's a suspicious cabin, but they can't conclude anymore. and they'll send this back in our inspection team functionality, and we'll do another mission. And we'll keep doing missions until we feel like we've clarified whatever it was. So that's how we stamp out our biases. And great idea about doing imaging on a place. Frequently we had to do a gamma backpack to walk around with its limited sensitivity to say, well, we saw nothing, so there was nothing to support the visual observation suspicion. Anyway, thank you.
Thank you. Okay. I had a question online, but it disappeared.
It was Harry's.
Ah, okay.
Yeah.
So, okay.
You clarified.
Any other questions from the floor? Can't see anything. No? Yes? Yes, please.
Yes, I also have a comment. Generally, also, I really like the panel discussion. A lot of interesting new new technology developments. I wanted to comment on the LiDAR point as well. I generally support the point of view. Of course, there's a lot of small-scale fluctuations that are currently not considered in models that affect our propagation. But some subtleties need to be addressed as well. This is particularly important during the periods around the equinox, when the middle atmospheric winds are very low. This is when the small-scale fluctuations play an important role. And moreover, even though the LiDAR can resolve a lot of these, the acoustic waves have such small wavelengths that they will be sensitive to small-scale structure that even LiDARs cannot resolve. So I think that remains a very important point. So even if you would put LiDARs all over the world, you wouldn't be able to simulate all the acoustic signals that are actually received. So in a way, you could also use it the other way around. Use the infrasonic observations as a way to constrain atmospheric models.
Thank you very much for these additional comments.
Can I just react to what Jelle said? Thank you, Jelle. So yeah, that's a fair point. So essentially with LiDARs, the vertical resolution you can achieve is a few hundred of meters, and depending on the LiDAR you're using, etc. So it's not only about gravity waves, it also goes down to turbulence, which is difficult to account for. And I think it's a fair point to state that there will be always wriggles in your atmosphere that you will not be able to resolve even with LiDARs. And so a few hundred meters will not be enough anyway to cover the full range of atmospheric perturbations that affect your acoustic waves. And yes, and we quite like the idea in the community to see whether infrasound observations could help constrain, as like using infrasound as tomography, basically to constrain the perturbations propagating into the atmosphere. So thank you for raising that point. Yes.
Any other comments, question from the floor? Yes, please.
So my question is on remote sensing and SAR in particular. We heard from Dr. Fry about space-borne SAR. I'm just wondering, do you think there's any value in deploying airborne synthetic aperture radar during an inspection or on-site inspection? Thank you.
Yeah, you have airborne systems with SAR sensors available. The problem is to have to bring it there, and in the context of the talk I had I was talking about the ground movement and the ground deformation measurements. The issue is that we have very high quality, and we see millimeter to centimeters movement from space, because the space signal is very stable. We have very good positioning systems to allow for accurate positioning of the different satellites we are using. So there are pros and cons on that. If you talk about surface resolution, we have higher surface resolution, of course, if we are using airborne, but we have also cons in terms of accuracy. And there are a lot of discussions, and we also did test SAR, which to use it, you know, more on-site based on UAVs, but quality, specifically if we are talking about surface movements, is at the moment still very low. So it's above centimeters, and it doesn't, you know, really bring us to this point. If you're talking about optical data, we have, and you want to really see what happens on the ground, also on the surface. You have hyperspectral sensors, and here we have even UAVs, which are operational, and also the methodologies behind it, and this is flown airborne also in an operational mode. So this would be my answer to your question.
Thank you, Michaela, for these explanations. Any other questions from the floor? No, I have none.
Yeah,
none.
there is one question.
I can't see. Sorry, I'm sorry. I can't see anything.
Good morning. Hey, thanks to the panel for a great discussion. My question is mainly geared at Jenny. I'm very curious to hear your thoughts as a third training cycle OSI inspector. What challenges are faced in the data fusion realms that these technologies present, and how can the inspectorate or OSI start to work to address some of those challenges as you bring these disparate data sets together and use them within the inspection team functionality framework? Thank you.
Thanks, Emily. Yeah, so that is one of the big challenges, I think, of all of these techniques. The data products that you generate are so disparate that it's actually very difficult to visualize them in a way that is coherent and gives value to the inspectors. The PTS has worked very hard on developing a graphical information management system, the GMO system, that will allow you to do this pretty effectively, actually, but you have to think incredibly hard as an expert in each of the techniques what data products you actually want to inject into the GMO system. For example, with the seismics, you know, are you going to have any kind of visualization of a waveform, and is that going to be useful to an inspector? Well, no, probably not. So then you think about, well, what we actually want to include in the GMO system are the locations of the events, the magnitude of the events, how can we kind of represent those visually, and then how do we overlay all these different technologies and techniques in such a way that you kind of have that incremental benefit every time you add a new piece of information, and then how does that then inform your inspection team functionality, your decision making, and things like that. And with these new techniques, you have new challenges. The kind of the data volumes are very high, and you know, how does your graphical management system kind of handle that? Is kind of the angle that we have to think about all these things through. So I hope that answers your question.
Thank you, Jenny. Thank you.
This one on the left.
Please, your turn. Yes.
Thank you very much. I want to thank you for these excellent presentations and this wonderful week. My question is concerning the way you are working together in your teams, and how and if different languages are playing a role. In case yes, which role does it play for team building, and also in the end for innovation? Thank you very much.
Hey, Jenny.
Who want to answer these questions? Jenny?
Yeah, I'll jump in on that. So in my experience, I think language and culture within the team definitely has an impact. And you have to be extremely mindful that you don't allow essentially English native speakers to dominate, because there's so much expertise within the team. You have to make sure that you're really drawing on all of that, and your leadership has to really ensure that they are, pulling out the best of everybody. And yeah, there are language barrier challenges, there are cultural challenges, but in my experience, the team always pulls together, and you get kind of a really positive outcome in my experience. But yeah, it certainly is a challenge. Thank you for your question.
Thank you, Jenny.
Maybe I just commented from my point of view. So at Leica Geosystems, we are a Swiss-based company, close to the border to Austria, in Herbruck, very little rural town, city, village, I would call it village, 2,000 people. We have over 100 nations working at Leica Geosystems in Herbruck. Different languages, different cultures, different persons, different behaviors, and I have to really say it's wonderful. The German-speaking community, which when I started 23 years ago was dominating, so we were all speaking German. Now it's English is our language. Other people are dominating now our lunch. So we have a big Italian group. Amazing and good fun to have lunch with Italians. It's again a little bit loud, but funny. So I think this diversity is a key factor, to be honest, a key factor for success. Diversity in people, diversity in cultures, because only with that you can see different angles. If we would always only be Swiss engineers looking from a Swiss point of view, I think our company would not be successful. So this diversity is a key element for success of a company in 2023.
Thank you, Johannes, for your experience. Any other question? I don't see anybody. Online questions? No? Then I would wrap up this session. I would start with thanking our panelists. This was very interesting presentations on these technologies. I would gather from what we've heard that what is important now is probably to assess the feasibility of all these techniques and the merging of these techniques into a global framework, which will be the responsibility of the PTS, I would say, to assess and to organize expert groups dedicated to what we have heard today as new technologies or expansion of existing technologies, because really a lot needs to be done. Their feasibility, their, I would say, their data fusion and the training of people of different languages, I understand, and different cultures. But it's really now within the hands of the PTS to organize expert groups within Working Group B or another framework in order to see how these technologies could be directly applied to the purpose of the treaty, meaning monitoring nuclear tests. So that would be my conclusion today. I thank the audience for being here, attending and raising questions and comments. It means that you are interested in what was presented. So thank you all. Thank you as a PTS for organizing this beautiful conference in this gorgeous building. And thank you all, and I wish you all a good lunch. Thank you.
Thank you.